Hi guys, this video describes some applications of stacks. We've already described what the stack data structure is and what its operations are. The next videos are going to explain how we implement stacks, but first we want to explain what we use stacks for so that you can hopefully appreciate why we're doing this. Intuitively, the point of a stack data structure is a hold that thought kind of situation. So that's where you are doing something, a task, and you can get an interruption that takes your focus away. And then when you finish with the interruption, you want to be able to pick up where you left off or go back to the task you were on before the interruption. So in order to model that in terms of the data structure operations, when we start a task, we push it on the stack. And that means the task we're focused on is always at the top of the stack. Whatever is on the top of the stack is what we're working on right now. The things below that on the stack are tasks that we're going to get back to later. And then when we finish a task, we pop it off the stack so it's gone, and whatever is currently in second place becomes the top of the stack. So that's when we resume whatever is at the old second place, the new top position. This corresponds to the last in, first out phenomenon. So when an interruption happens and takes our focus away, that's the most important thing right now. But then when we're done with it, we want to go back to the last in task, or the most recent task that we had started is the most recent thing on our mind. So to illustrate this, I'm going to write what I know and tell a little story from my real life that might correspond to this. So after final exams happen, I spend 1 or 2 whole days in my office grading exams. So let's say it's one of those days I have a task for the day, which is to grade hundreds of final examinations. So this stack over here represents my tasks that I'm focusing on. So the 100 represents grade exams. It's at the top of the stack. So that's what I'm working on right now. Let's say I work on it for a couple hours and I need a break. So I decide I'm going to go get some coffee. So I walk over to the cafe on campus and I'm starting a new task. So I push the coffee task onto the top of the stack. What that means is right now I'm working on getting coffee, but when I'm done with coffee, I plan on going back to the exams. So the exams are in second position, but the top of the stack, my focus is the coffee project. Let's say I get to the cafe and an acquaintance is there and they want to make some small talk while we wait for our coffee. So now I refocus. I'm not really focusing on the coffee thing. The top of the stack is this conversation, but I still have in the back of my mind when the conversation is over, I'm going to go back to finishing my coffee order. And when I'm done with the coffee acquisition, I'm going to go back to the exam grading. So the conversation winds down. I pop the conversation off the stack, and now my focus goes back to the coffee. I collect my order, and the coffee task is over with, and now it's time to go back and finish the grading. So that's a delightful little story, but let's see how the same kind of idea can apply to computing applications. I'll be honest with you here, most of the applications of stacks are as part of an algorithm that is outside the scope of this class. There are few features in software that correspond directly to stacks. Our next data structure is a queue, and there are lots of practical examples of queues that you work with, such as playlists. So those are easier to motivate, but frankly, stacks, we have to dig a little bit deeper. So please bear with me here on these applications. They're a little less intuitive, but do take our word for it, please, that stacks are important. While it's not immediately obvious right now how they get used, they are important and will get used quite a lot soon in your career. So please have some trust in your instructors and the curriculum that it is well designed and stacks are worth learning about. There are 2 themes in these applications. One is that kind of task tracking with an interruption and refocusing corresponding to pushing and popping that I outlined a moment ago. And the other is a feature that just naturally uses the last in, first out ordering. The first example is one of those that naturally corresponds to the last in, first out ordering. That's the back button on a browser. So that follows last in, first out because when you press back on a web browser, you go to the most recent web page. So you don't go to the first web page you ever visited, you go to the one that's most recent in time. You know, if I click a link, click a second link, click a third, click a bunch of links, and then I click on the back button, we go to the most recent one. So that's last in, first out. If I click back a second time, I go to the second most recent one, meaning the web page I was on before the most recent one. We can represent this kind of web browsing history as a stack data structure. When you visit a page, you push it on the stack. So that means the top of the stack at all times is the web page I'm on right now. In order to go back, I pop the current web page off the stack. That means that the new top of the stack will be the previous page I was on. So the new top is the one we need to go to, so we go there. That's how we go back. A similar application is the undo button in a word processor or text editor. Those have an undo button. It's kind of similar to the back button. It also follows this last in, first out ordering. So when you undo, you want to restore the most recent version of the document, not the current one we have now, but whatever we had before I did the most recent thing, like typing or deleting or something. And you can undo a second time, and that gives you the version before that. And if I undo again, it's the version before that, and so forth. So again, we can represent this edit history as a stack data structure. When you make an edit, like typing something, we push that change onto the stack. So we have a stack of some class that represents a editing operation, and the top of the stack is the most recent change that was made. In order to undo, then we look at the top of the stack, and the top gives us one of these change objects, the most recent changes that were made, and we reverse it. So if the most recent change was to type the word dog, we delete the word dog back out again, and that gives us the version of the document we had before typing dog, and then we pop to take that part of the history away. Okay, another application is that stacks are used usually in the depth first search algorithm. This is really so this is an algorithm for traversing a graph. This over here is an example of a graph. It's these sites called vertices with circles and these edges drawn as lines. This is really an advanced data structures topic for later in a course like this or in an algorithms course. So like I warned, this is kind of beyond the scope of the class. I can't really explain this thoroughly at this point, but basically the idea is that this algorithm uses a stack as a to-do list of the unexplored vertices. This algorithm explores the entire graph one vertex at a time. In order to do that, it needs to keep track of where it's been and where it hasn't been and what still needs to be explored. And a stack data structure is used to keep track of what needs to be explored still. Another application is parsing context-free languages. These are data formats with nested delimiters. For example, open and close parentheses, open and close braces, HTML tags. All of these have this format where you start a delimiter and then it needs to be paired off with a close delimiter. So as you know from programming, every time you open a parentheses, you need to have a corresponding close parentheses or else the syntax is invalid and the computer doesn't know what you mean. So that would be those kind of programming formats, but also data interchange formats like HTML, JSON, XML. They all have this structure as well with open and closed delimiters. This is really a topic for a theory of computation course. That's where this context-free language terminology comes from, or compilers implementing parsers for computer programming languages. So again, I can't really get into all the details at this point, but you should know that software to parse these kind of languages uses a stack to track the currently open delimiters. So every time a delimiter goes open, we push it on the stack, and when we see a closed delimiter, we pop it off the stack. If the stack is empty at that moment, that meant there were too many closed delimiters. We had some closes that didn't have corresponding opens, and we can issue a compile error. At that moment, if we get to the end of the file and there's still open delimiters on the stack, that means there were too many opens, and we can issue a compile error for that reason. So if we wanted to parse this complicated if statement, for example, what a parser would do is have a stack for currently open parentheses. It would be empty to begin with, and then, oh, I see an open, so push that, push, push, and then I see some stuff that's not parentheses, and then when we get to this close, that means I can look at the top of the stack and figure out this open here is the parenthesis that corresponds to this close. And we can factor that into how this I greater than 0 is interpreted by the compiler, and then pop this open off because now after dealing with this open and close pair, there's only two currently open parentheses. Finally, a very practical application of stacks are implementing function calls. This is kind of a topic for an assembly programming course, so again, I'm not going to get into all of the details here, but what I want to tell you is the idea that the way that a runtime deals with calling functions and returning from them and knowing where to go when that happens is using something called a control stack. So when you call a function, the program jumps to the body of the function. When you return, we jump back to where we were previously. That going back to where we were previously is a last in, first out ordering, and the stack is the right data structure for that. This is the original reason for quote unquote the stack was to handle this. So in C++, we have all this stuff with the variables on the stack and so forth, but the original impetus for creating something called the stack was to implement the function call jumping. When you call a function, what you do is push the current instruction pointer on this control stack. The instruction pointer is basically where we are in the program. It's the location of the current line of code we're executing. So I've got a little function over here, L1 distance calls absolute value. So if you are in main and you call L1 distance, you push the line of code you're on in main onto the control stack, jump to L1 distance's body, run until we get to the next function call to abs, absolute value. So we'd push the current location, we're on this double dx line, push that onto the control stack, go run abs. When abs returns, we pop off the stack and jump back to where we were previously, which is finishing this double dx line. So stack is used internally in the implementation of function calls. We don't have access to it directly as like a class, like a data structure, but the same LIFO push pop top operations are used there.